A process is called totally reversible or reversible if there is no irreversibility, okay, within or within the system or its surrounding. So basically what it says is that for a process to be reversible, it needs to be both internal and as well as externally reversible. Okay, if it is internal and not external, it is not reversible. And similarly, if it is external and not internally reversible, then it is not reversible. Okay. Now, this we have anyway discussed. Yeah, this slide we discussed yesterday. Okay, anyway, I'll just go through it quickly. So, process is called reversible if it is performed in such a way that the system is always very close to equilibrium state. Okay, at all the time. So basically, we are talking about quasi-static process. So it is a quasi-static process plus no dissipative effects are there. Okay, in any form. Then it will be classified as a reversible. And another important thing that you must understand is that a reversible process is a very idealized process. Okay, it is a limiting case, and it is only possible in theoretical cases. So it is, and whenever I talk about a reversal process, I am mostly talking about theoretical approximation. Okay, but all natural or practical processes are essentially reversible. But taking a theoretical consideration, taking an ideal limit helps us to approximate a lot of natural processes, and it helps us to solve numericals and get values for work, heat transfer, which are approximate in nature. Okay, but it is still better than nothing. We can idealize and we can get some theoretical estimates. For example, we can use second law and tell what is the maximum efficiency that an engine could have. Okay, so this will be more clear when we talk about numericals. Let us now this Carnot cycle we have discussed it today. I just wanted to repeat it quickly again because this is a very important topic for this chapter as well as your subject. Okay, so we have seen this cycle yesterday. It has four processes: two isothermal, where temperature is constant, and two isotropic. So these are basically reversible adiabatic. So if you have reversible adiabatic, this is called isentropic. So entropy we'll study in the next chapter. Basically, you can understand that it is a reversible adiabatic process. Adiabatic means that there is no heat transfer involved. So for that, what we do is we have a piston cylinder arrangement, and we assume that the side of the pistons are insulating. Okay, so this wall, basically we are saying that this wall is conducting, and we can either use it to conduct heat or we can insulate it. Okay, so when we have isothermal heat addition, we will not insulate it and use it for heat transfer. Second step, when we have adiabatic process, so it will be insulated, so there is no heat transfer. So I am assuming that these sides are all insulated always. So there is no heat transfer from other sides, and this expansion goes on in adiabatic mode without any heat transfer from the surrounding. That is the meaning of adiabatic. Okay. This is your second process. Third is this is contraction because of heat rejection. So the system goes back to 4. Now the last step is isentropic or adiabatic compression. So the system finally goes back to the initial state 1 where we have started. So as you can again verify that what we said according to the second law, that the system needs to have two reservoirs, okay, TH and TL. That's how it will go back to the initial state. If you remove any of the reservoir, it will not be able to reach back to its initial state. It will not be able to complete the cycle. Okay, so that is what is required, and that is how it is following the second law. It has at least two reservoirs. If it is possible to design a cycle where you can have more than 2 reservoirs. You can have 4 reservoirs, but you cannot have a cycle where you have only 1 reservoirs. So you cannot remove either the source or the sink. Both have to be there. It is not possible if I remove any of them. Okay. So this is the like basic of second law. Now these are the various processes that we have discussed yesterday, and I was trying to emphasize on isothermal heat transfer. So in next chapter, when we talk about gas power cycles, you will see that this is what is makes Carnot cycle different. Because of isothermal heat transfer, it becomes both internally and externally reversible. So this process is truly reversible in that sense. Okay, so this will be more clear when we discuss other cycles. But for now, you can note down that this makes Carnot cycle most efficient. Okay, it is anyway difficult to achieve. So this is again a theoretical approximation that we are doing isothermal heat transfer. Okay, moving on. So let us talk about reverse Carnot cycle. So this is what we have seen. Okay, heat engine. Okay, anyway, tell me one thing that we have discussed this previously before talking about the second law. Now we are talking about Carnot cycle. So what is the difference in this? What we discussed previously and what we are discussing now? Can anyone tell? Is there any difference or no difference or any additional detail is available now? People are here.
Yes, sir.
Can you please repeat the question?
So my question is that okay. So my question is that previous slides also, before talking about the second law, before talking about the Carnot cycle, we have talked about heat engine, right? We have discussed heat engine to define Kelvin Planck statement. Now
Yes,
again
sir.
talking about the same heat engine. So is the heat engine same or any difference that you can see? Okay, let me answer. So the heat engine is same, okay, but when we discussed previously, when we discussed before defining Carnot cycle, what I said was that this is the overall effect of the engine. The engine works on any cycle, and this is the net effect that it is transferring heat from high temperature to low temperature, and it is doing some work. Okay, that time we didn't paid attention. We didn't bothered what cycle it is running on. That time I just mentioned that it runs on some thermodynamic cycle. Now we know that when we are talking about Carnot cycle, and I'm showing in this plot, so which means that you have one additional detail now. We know that it runs, this engine, heat engine runs on this cycle. Okay. Earlier, when in general I'm talking about a heat engine, then it could be running on any cycle that I don't care of. Mostly in numericals, you will have numbers that okay, this much heat is coming out or what temperature is there. If no more detail is given, it means that you need not worry what cycle it is running on. But here we have one additional detail. What is the detail? That this is the cycle it is running on. Okay. Is it clear to everyone?
Yes. Yes, sir.
Fine. So this is what we have already discussed. This is your Carnot cycle. Now let us talk about reversed. Reversed mean all the processes will be in reverse order. What we'll have is your first process will be 1 to 2. This is reversible adiabatic expansion. So this is expanding. Earlier we had 1 to 2 like this. Now we have, let me get a pen. Okay, earlier we have 1 to 2 like this. Now we are going in this direction. We have reversed the cycle. So what is the net effect is that anyway all the processes are reversed, that you can verify from these two plots. But the net or the more interesting effect is that earlier this cycle was producing work. We have net work which is output. Now the cycle is requiring work. Okay, so the net effect of the cycle is that it requires work as an input to be run. Okay, so now you see the difference. This is the heat. engine, this could be a heat pump or a refrigerator. Okay, so now it is transferring heat from lower temperature body to higher temperature body, and it requires work as an input. And you see the difference in symbol. So it was earlier clockwise because this is how it looks in a PV diagram, and this is anti-clockwise now. You see in this direction, because that is how you are running in this cycle in a PV diagram. Is this clear to everyone?
Yes, sir.
Yes, sir.
Fine. So let us now define Carnot's theorem. Okay, so what Carnot proposed was that of all heat engines operating between a given constant temperature source and constant temperature sink, none has higher efficiency than a reversible engine. Okay, so this is the historical statement what Carnot said. Now we'll try to understand what exactly he meant or how we can interpret. So what he's trying to say is that for a given TH and TL, suppose this is fixed, then a reversible engine will have the maximum efficiency. Okay, so if you fix the source and sink temperature, and if you have a number of engines operating between them, that could be reversible or irreversible, then the reversible engine will have the maximum efficiency. It will have anyway more efficiency than irreversible. And another consequence is that, or in other words, we can say that all irreversible engines will have lower efficiency than reversible engine. Okay, so this is quite obvious because any irreversible engine will involve losses. It will involve dissipative effects. So your efficiency will anyway come down. So that is not there in a reversible engine, and it will have higher efficiency. Right? Now this Carnot's theorem has a very interesting outcome or a corollary. So what is the corollary for Carnot's theorem is that efficiency of all reversible heat engines operating within the same temperature level is the same. Okay, so what we said in the last slide that reversible engine has maximum. Okay, so I don't define what cycle it is working on. So the consequence is that any cycle, if you have a reversible engine, if you have a fixed temperature limits, then it will have the same efficiency. Okay. Now the efficiency of a reversible engine is independent of nature of the amount of working fluid. This is also a consequence that any fluid or any mass of fluid you use, the efficiency of reversible engine will be maximum and it will be higher than irreversible engine. Okay, is this clear to everyone?
Yes, sir.
Okay, so now I can define efficiency. Suppose if I have an engine, I don't know it is reversible, irreversible, what it is. I'll measure the thermal efficiency of that. Now, if that efficiency is less than that of a reversible engine, okay, so I'll compare this efficiency with a reversible engine efficiency. So if it is less, then of course it is a irreversible. If it is equal to a reversible engine efficiency, then it has to be a reversible engine. Otherwise, it cannot be equal to. Okay. Now, if that efficiency is more than a reversible engine efficiency, that is simply not possible. That violates the second law. Okay. So, if you compare efficiency of any engine with a reversible engine, you can determine whether it is reversible, or it is impossible to have. Okay, moving on. So let us talk about absolute thermodynamic scale. So a temperature scale that is independent of the working fluid. Okay, independent of the properties of substance that are used to measure temperature. This is called thermodynamic or absolute thermodynamic scale. Okay. Now, Kelvin proposed a temperature scale such that, so basically you take a heat engine, and the heat transfer is proportional to the temperature limits, the fixed temperature. That is the basic idea behind Kelvin scale. Okay, so you understand what I'm saying? Basically, how much heat you are getting from TH, that will be proportional to TH if you define TH in Kelvin scale. Okay, and also you give a fixed point of 273.16 Kelvin for triple point of water. So Kelvin scale is basically designed in such a way that heat transfer is directly proportional to that temperature, the numerical value of that temperature of that body. Is this clear to you?
Yes, sir.
Sir, is this scale only
Yes.
theoretical or practical also?
No, Kelvin scale is practical. So basically, we define this for a reversible engine. Okay, but Kelvin scale we have, for example, you will use it in numericals. So we have Celsius scale, we have Celsius scale, we have Fahrenheit scale, and similarly we have Kelvin scale. So Kelvin will be 273 plus Celsius. For example, your room temperature. So suppose your room temperature is 30 degrees Celsius.
Yes,
Okay.
sir.
So in Kelvin it will be 30 plus 273.
Okay, sir. Thank you, sir.
One thing I want you to be very careful about. See, when you talk about when we go to numericals, okay. So this relation U is proportional to T is only valid for Kelvin scale. Okay, so you will get numericals where the temperature will be given in Celsius or Fahrenheit. The first thing you are supposed to do is convert that to Kelvin. A lot of students do that mistake. So I want you to be careful about that. Okay. Whenever the temperature is given in Celsius, just add 273, get the Kelvin value and use that. Otherwise, it will be wrong. Other scales are not proportional like this. Okay. Now let us
Sir, but how will be finding
yes.
out the efficiency for irreversible processes?
Sorry, please repeat your question.
Sir, how will be finding out the efficiency for irreversible processes?
See, when we talk about numericals, we will most likely be dealing with the reversible processes. For irreversible, we'll say that some losses are involved. Then we can, if you can quantify that losses, then you can calculate the efficiency. Otherwise, we'll limit ourselves to reversible. So we'll approximate that. Let us say it is a reversible engine, and we'll calculate the efficiency. So
Because sir, if we take in the last slide, we showed that
yes,
efficiency for reversible is always
yes,
greater than
yes,
irreversible. But as if both the temperatures will be always same and heat will be always liberated out. So how can
yes.
we?
Okay, so let me tell you. So this is, let us say that this is a heat engine. This is how it runs for a reversible cycle. Okay, so for a reversible cycle, I will expect my net work output to be QH minus QL, right?
Yes,
Now
sir.
I have irreversibility is involved. I will also have to remove, let us say W dash or some factor. So the net work output will be less than what we get for reversible. So when you get a numerical, this either this will be quantified or let us say heat transfer will be different. It will not be same. So some difference will be there. Basically, how you design your numerical or how you define your engine, some difference will be there. Then based on that you can calculate. Okay, so mostly the numericals that we will be dealing with will take a reversible engine and we'll also quantify what if some heat loss is there or some friction loss is there. That we'll see. So I will suggest that you look at the numericals. Once we discuss that, it will be more clear to you. We can discuss this again.
Okay, sir.
Okay, now coming to Carnot cycle efficiency. So this is how we have defined the heat engine. This is how we define how it is running on the Carnot cycle. Now the thermal efficiency we define as net work output divided by total heat input. Okay. So what is the net work output here? W net, and heat input is QH. So we can define W net as 1 minus QL by QH. Is this okay? This we have previously also defined, I believe.
Yes, sir.
Yes, sir.
Okay. Now let us. So I want to derive this is equal to 1 minus TL by TH. So this is what we should expect based on the definition of Kelvin scale. Now this equation I want to derive using theoretical considerations. We'll talk about the work done in all these four steps. Work done, heat transfer, we'll discuss. Okay. So now for isothermal heating process 1 to 2. 1 to 2, let us talk about what is the heat supplied, what is the QH. Okay, one more thing I just wanted to mention. So in this plots, you can see that we are mentioning P and this is small v. So this is specific volume. Okay. So for such plot, I will define small q. This is intensive. But if you multiply this by mass, we'll get capital Q. So these are very small finite details that you need to be careful about when you want to talk about specific or intensive properties, and when you want to talk about total or extensive properties. So both are okay. We can talk about small q also here. We can talk about capital Q also. But you should just be clear what we are discussing. Okay, so when we talk about capital Q, it means I am talking about, I am considering the total mass, then I will talk about the total volume. I will not talk about small v, I will take capital V. Okay, so let us try to find out what are the work done and heat transfer involved in these processes. Okay, so for isothermal heating process 1 to 2, we have that will be equal to work done. Okay, in that process, which is equal to, you have studied this in I think second chapter when we tried to find out work done for different processes. So if you go back to that slide, you will find that this is the work done for isothermal process.
Yes,
RT
sir.
log V2 by V1. Okay, now note that this is capital Q, capital W. That is why this is capital V. Okay, so for isothermal heating process, we have heat supplied is this much, which I can call it QH. Okay, now for cooling process, let us first look at isothermal. Then in the next slide, we'll talk about adiabatic processes. So for isothermal cooling process 3 to 4, where it is? It is here, 3 to 4. So Q3 to 4 will be equal to W3 to 4. Similarly, it will be RT log V4 by V3. Okay, and this we can call minus QL because this is going out. This is getting removed from that system. Okay. So this is for isothermal. Now let us go to isentropic processes. Or QL, we can also note it like this. We can reverse the volume. So log sign will be reversed. So minus sign we have removed in such a way. Now let us go to isentropic processes. So for isentropic expansion, so isentropic processes, or let us say adiabatic process, can be noted down as P, or let us say P V to the power gamma is equal to constant. Okay, so in last lectures on work done on basic processes, we have also talked about polytropic processes. Okay, so if you go back to that slide, you'll see that for polytropic process, this is how work done. So for polytropic, we have used N. Okay, for adiabatic process, N is equal to gamma. So gamma is the ratio of your Cp by Cv. So this is the relation that holds good for adiabatic processes, and this is what we are applying here to relate volume to temperature. Is this clear to everyone?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, so let me just delete it so that I can get the next sequence. So this will, I can write it as TL by TH, right? Because T2 and T3 are, T3 and T2 are TL by TH. If you notice in this plot, T2 is TH, T3 is TL. So similarly for isentropic compression 4 to 1, this process, again I can write T4 by T1, 1 minus gamma minus 1. This relation again you can derive using this PV is equal to constant and PV is equal to an RT. So this will be again can be written as TL by TH 1 by gamma minus 1. So based on these two relations, what we can say is that TN and TH are common. So I can write V2 by V3 is equal to V1 by V4. Is this okay?
Yes, sir.
Now based on that, I can say that V2 by V1 is equal to V3 by V4. I've just changed the order. Right? Now I have Carnot efficiency as 1 minus QL by QH, which can be written as 1 minus RT log V3 by V4, 1 minus divided by 1 RTH log V2 by V1. So this is what I got from the last slide when we derived the relation for isothermal processes. Okay, I will go back if you want. So there we have defined QL. Basically, we have found a relation for QL and QH. This is what I am using there. Okay. So we express QL and QH in RT log volume ratio. Now volume ratio can I replace from here? So what I see here is that V2 by V1 is equal to V3 by V4. Right? So can I cancel these two? I will be remaining with. So basically, if I cancel, let me get to that stage. So V2 by V1 is equal to V3 by V4. Right? So I can cancel this log from numerator and denominator. I can cancel R. So I'll be remaining with 1 minus TL by TH. This is your Carnot efficiency. So again by theoretical derivation we have shown that QH by QL is equal to TH by TL, and this relation holds good for Kelvin scale. Okay. Moving on. Now there is something interesting based on this equation. So this is what we need to we use to calculate for Carnot cycle. Okay. Now we see that this efficiency is dependent only on TH and TL. It depends on the higher and lower temperature limits. So what we can do is that we can take a, let me get a pen. So we can take a cycle, okay, and we can fix the TL to 303 Kelvin. Okay, don't look at this, just focus on this. So for a fixed TL, if I keep on changing the TH, I will change the higher temperature. Let us set to 925, 800, 350. And using this equation, if I calculate how much thermal efficiency I am getting. So you can do this calculation and verify that for TH we are getting 67% efficiency. For TH of 350 I am getting 13% efficiency. Right? So you are basically changing this TH in this equation. TL remains constant, one is already constant. Is this clear to everyone what I'm trying to do here?
Yes,
Yes,
sir.
sir.
Fine. So using this example, what you can see is that basically we are getting more percentage of work, more percentage of heat energy that can be converted to work. Okay, higher efficiency means that here I am converting 67% of heat to work. Here I am converting 13.4% heat to work. So it is better to have energy at a higher temperature. It is always better to have energy at 900 Kelvin as compared to 350 Kelvin. And the higher the temperature, higher is the quality of energy. Why? Because higher proportion of that energy you can convert to high grade energy, which is work. This is also very interesting aspect of quality of energy, which is coming out from the thermal efficiency of Carnot cycle. Any questions on this?
Sir,
No, sir.
sir, I have a question.
Yes, please go ahead.
Sir, why we cannot have 100% efficiency even
The
after
thing is,
not having any kind of dissipative losses?
okay, good. So this, were you present yesterday's class?
Yes, sir.
So that is the essence of second law. The second law
So, sir,
basically, if you go to those two statements, let me finish. So if you go to the statement, both are. So if you, for example, talk about Kelvin Planck statement. So Kelvin Planck says that you need to have at least two reservoirs, two thermal reservoirs. Okay. So you cannot remove either source or sink. So if you're doing that, then you need to, one reservoir will supply you heat, one reservoir you are basically rejecting heat. That is what we discussed. Let's go back to that slide.
yes, sir, I remember, sir.
So why you have doubt now? This
No, sir,
system.
I mean, where does that extra thing go? Extra heat? Why it
So
cannot be converted?
we are throwing it. So for example, if you have let us say let us talk about IC engine. Let us say you have a car
Yes,
engine, but
sir.
okay. So some exhaust is coming out, right?
Yes, sir.
That exhaust gases are at much higher temperature than the atmospheric temperature, right?
Yes, sir.
So you are throwing that to the atmosphere. You cannot say that my losses are zero or the heat transferred. So for your let us say for your scooter engine or for car engine, atmosphere is your sink. Atmosphere is your sink. So you are throwing heat to the atmosphere. So you cannot say that you will reduce that. Okay, theoretically it is not possible. If you extract all the amount of energy from that exhaust gases, okay, then you can say QL is equal to zero and your efficiency will reach 100%. But that is theoretically not possible. That is not something which is not allowed by the second law.
Okay, sir. Sir, you also said that some means we also have to complete the cycle, so that's why we cannot
Yes,
achieve 100% efficiency.
yes.
So,
So
sir, can I think like if you consider an internal IC engine, then
yes,
the piston needs to go down. So some energy is required for that purpose to complete the cycle.
actually I should not have used piston. It is not a very good. Your car engine is basically an open cycle. Okay, so we'll come to that. So let us talk about Carnot cycle. Okay, so basically what happens is in your car engine, it has to exhaust gases and then it gets fresh charges.
Yes, sir.
Okay, so it throws out some energy, but so it is actually an open system. It is not a closed system, but we generally model it in a closed system. We'll talk about in the next chapter when we go to that particular topic. But let us talk about the Carnot cycle. Let us, as you see in this plot, it is a closed system, right? The gases are hold fixed.
Yes, sir.
Okay, so the gases are not going out or coming in. So the mass of the gas is constant. Now you see that the gases are getting heated up. So we heat the gases, we did get some work from that. But finally, when I want to return to state one, because I have to complete the cycle, so I remove some heat. Remove some heat from the gas. Otherwise, it will not go back to the original state.
Yes, sir. Yes, sir. Got it, sir.
Okay. So that
Yes,
is
sir.
actually the essence, that is the outcome of the second law. You cannot have 100% efficient engine. Some heat has to be lost, and that heat we are not talking about dissipative effects or some heat. Theoretically, even for an ideal cycle, you cannot have 100% efficient engine. I think I mentioned it somewhere on the slide. So you just go through the slides. You'll find some more comments, and if you still have doubt, then we can discuss in Monday's class.
Okay, sir. Okay, sir.
Okay, so we have talked about where we were there. Okay, yeah, let me. So we have discussed about this, and we have found that we are getting. Okay, this is what we discussed. Now let us talk about reversed Carnot cycle COP. Okay, so the same heat engine, if we reverse, it will become a heat pump. So here we are taking heat supply and we are transferring heat from low temperature to high temperature. Now, what is the COP? COP is basically what we have defined is desired output divided by what is the required input. What is required to achieve that output. So we define COP differently for heat pump and refrigerator. For heat pump, the COP is QH by W. For refrigerator, the COP is QL by W. What is their major objective? What is that they are trying to achieve? Okay, so based on that, I can simply refer to this COP in temperature terms. Okay, so here for a heat pump, Carnot heat pump or any heat pump, any reversible heat pump, the COP of heat pump will be TH by TH minus TL. Similarly, for a reversible refrigerator, COP will be TL by TH minus TL. So this is the only difference between heat pump and refrigerator. Now, if suppose I have a refrigerator and I measure the COP, how it compares with COP of a reversible refrigerator. So if it is less than that of reversible, then the test case is a reversible refrigerator. If it is equal, then it has to be a reversible refrigerator. If it is more than the COP of a reversible, then it is impossible. It will violate the second law. Okay, so it could be at max equal to this or less than this. Fine. Is this clear to you?
Yes, sir.
Yes, sir.
Okay. So with that, we come to end of this second law, and these are the reference book. Let me stop recording for this. Okay.